Hi, welcome to the last part of this chapter on characteristics of measurement systems. So the last part, we're going to talk about some parts about biomedical measurements because that is our um, thing that we have to do. So in biomedical measurements, all the biosignals are actually very, very small. So the values, for example, the voltages that we can measure from our body is actually in the microvolts range to the millivolts range, which is very, very small compared to non-medical parameters, such as industrial equipment that we have. It could be in the volts to the kilovolts range, tens of volts range. So the pressure that can be measured in our body could be less than in mmHg to 400 mmHg. The frequency that our body the signal that our body produces are in this subhertz range, which is in the 0 point something range, all the way up to the 10 kilohertz range. So we are very problematic because we are somewhat constrained because some of the crucial parameters, you have to do some damage or what we call invasiveness to the body. So for example, if you really want to find out the blood pressure of a person, you have to go into the blood vessels to measure, which means you have to go into the body. Apart from that, parameters that we measure vary from person to person, and different time of the day you get different kind of readings. For example, your blood pressure when you wake up to midday to end of the night. If you were to measure this um, throughout the day, you will find that these three readings will definitely be a bit different. Next, because of the different feedback loops that exist within our body, there is, if you try to measure a certain part of the body, because of this feedback loop, it will actually compensate and affect the different readings that you have when you measure. And the next thing is the interrelationship between the different systems. You don't know what's happening between them. So when you don't know the system, how this would affect the other one, you will have a problem on trying to see whether your measurements used is actually correct. Next, let's talk about the norms. Okay, it is what we know as the statistical mean, which means I can only get a sample of everyone and we try to get a little average. And from there, we kind of like take it as the norm of a group, okay? Because it is impossible to measure everyone and every single one in this world and get the average. So we have to do what we call a sampling because we are unable to get the whole population. Okay, getting a whole population is technically impossible. So, however, these are actually just considered to be normal. For example, your heart beats at 60 to 110 beats per minute. That is considered normal because we use a sample. And if we were to get a reading of more than 110, we say you have tachycardia, which means your faster heart rate. Okay, and if you have less than 60, you have slower heart rate. Both are considered kind of like disease, so you have to go and check it out. but that might not be the case. So I need you guys to discuss this. Why is it that although although this is norm, these values are considered norms, but sometimes we cannot take that value. We can't take it at face value. Why? So I need you guys to comment this in the comment section of this video. Okay. I hope you guys would actually do some commenting and get a bit of discussion going on. Next, let's talk about electrical shock in measurements. So when everyone has actually got shocked by electricity before, right? So in measuring a human being, we have to design it carefully. If not, you'll get shocked. So one of the greatest danger is the electric shock when the current flows from the plug and into the fault, going to the chassis, going to the body, and down to the ground. But if it were to go into the heart, it might stop your heart. Okay, so when your heart starts to not function, you die. Simple as that. Although there are some natural factors that protect a person from electrical shock, for example, your dry skin, it has very high resistance, okay, in the mega ohms range. However, if it is wet, it is only 1%, and that would drastically, which means from dry to wet, you have a decrease in 99% of your effective resistance of your body. And if, since we're talking about electrical context, for example, if you're trying to get the ECG, we sometimes have to use the electrode gels. And also, there are a tank body fluid contacts, okay, something metal that's in contact with your body. That will also reduce your protection. So, if there is a need for us to use electricity, which is like everything, we have to make sure that it is electrically isolated. So there are three ways. Okay, the three ways are use batteries instead of using the mains, which means from your normal plugs. Next, we make sure that the front end, which means the one that is to be contact with your body, make sure they are electrically isolated. Last but not least is to make sure that you are using isolated main power supply, which means if you remove the current flow path through the patient, which means it will be isolated away from the patient. So these are all the ways that you can help to prevent uh, electrical shock to the patient. And in the front part, we talk about what we, uh, why do we have to do that. And with that, I'd like to conclude this whole chapter and say this is all the things that you need. If you have any questions, please bring it up. and